Hey guys, this is section 2.5, implicit differentiation. Go ahead and write down this FLT here. Pause and play whenever you're ready, okay? Okay, so given an implicit equation, you're going to be able to differentiate it by applying the concept of what we call differentials, okay? So before we do that, let's quickly recap here, okay? Go ahead and write this down. And what I'm going to have you do here is, from memory, I want you to write out what the product rule is, the quotient rule, the chain rule, and the three cases of differentiability. Cases where you cannot take a derivative, okay? So I'm going to give you as much as you need, but go ahead and press play whenever you're ready. And only if you need to look back, but try to recall from memory here, okay? Okay, so the product rule, F times G. So whenever you have a product, we apply the product rule. So it's the first times derivative of the second plus the second times derivative of the first, okay? Quotient rule, aka Drake's rule, right? You guys laugh now, but it'll stick. The quotient rule is you start with the bottom times derivative of the top minus the top times derivative of the bottom all over bottom squared. Okay. Chain rule is when you have a composition, when you have an inside function and an outside function. So if we take the derivative, why does it say D over? That's weird. Okay, so when you're taking the derivative of a composition or a function inside of another function, you take the derivative of the outside of the same inside times derivative of the inside. Cool, okay? Differentiability, there are three cases where you cannot take a derivative. The first one is a corner or a cusp. So pretty much whenever you have a sharp turn at that corner only, or at that moment where that corner turns quickly, you cannot take a derivative there. But you can take a derivative everywhere else, so keep that in mind, okay? Another location where you probably cannot take a derivative is at a discontinuity. Okay, so pretty much you wouldn't be able to take the derivative at where it's discontinuous. So pretty much right here or here, you can't take the derivative there because tangent lines are supposed to be unique, right? And based on this one, I mean, don't draw this out here. You could draw an infinite amount of tangent lines there. And tangent lines are supposed to be unique, right? And the last case, hopefully you remembered, is when you have a vertical tangent. This one doesn't pop too often, but when you have maybe a function that looks a little bit like, whoa, like this, where you might perfectly have a vertical tangent there, okay? You can't have that because a line that's vertical has no slope because it keeps rising and it never runs. So you're dividing by 0. Keeps rising, but it never runs. So that's why you can't have a vertical tangent, because there really is no slope there, okay? Make sure you guys understand that saying a slope of 0, a 0 slope, is not the same thing as saying no slope, okay? No slope means that it's a vertical line. 0 slope means that it's horizontal, all right? Okay, so that's a little bit of a recap. Hopefully you guys were able to recall that without having to look back at your notes. But again, the only way to get better is to keep practicing and saying it over and over and over again, okay? Okay, so before I show you guys what implicit differentiation is, we want to know what the heck is implicit, right? So here's some examples, okay? Y equals the square root of x cubed plus 1, or y equals x times sine x. These are what you call explicit. Okay, now y, right? WHY. So here's what you notice. You notice that a variable is always isolated. Okay, that's how you can tell that it's explicit. But also, on the other side, there's only one variable. Okay, notice how the right side is just in terms of x. All right, so one more, y equals x squared plus 4x plus 3. That's also another explicit function. In most of math, we deal with explicit equations. You guys are used to it, where usually y is by itself. Okay. Okay. Now, here are some examples of implicit equations. Okay. X squared plus y squared equals 25. X cubed plus y cubed equals 6xy. So I wrote it down here, but basically you notice that there's no variable that's isolated. That's one. But also you notice that there are multiple variables, right? Multiple variables. So sine xy equals y. Even though this right here is isolated, the other side has multiple variables. So when you have multiple variables on one side of the equation, it's an implicit equation. Okay? So we're dealing with kind of the gross equations that have multiple variables. Okay? So really this whole unit, you guys, you're learning how to pretty much differentiate anything. Okay? So there's this concept of what we call differentials. Go ahead and write this down. A differential is basically when you take the derivative but with respect to that variable. Okay? This is what we call Leibniz notation. I hope I'm spelling this correctly. Leibniz notation. You guys are used to Lagrange notation. Lagrange notation is pretty much like y prime, f prime of x, g prime of x, right? But remember, Leibniz notation can also express derivatives. We use dy over dx, ds over dt. It's really the same thing, just written a little bit differently, all right? So we're going to use Leibniz notation, which means the exact same thing. So here we go. So here, think about whether that's explicit or implicit, okay? Play when you're ready. This is definitely explicit, okay? So explicit here, we can just find the derivative the same way, but I'm going to show you how differentials work here, okay? You guys have been doing differentials. It was just a hidden step that you've never seen before. So here's what you do. Suppose that y was a variable, okay? The derivative of y is just 1, okay? But with respect to y. So for instance, if I ask you guys what the derivative of 5x is, you guys would say 5. The derivative of 3x is just 3. The derivative of x is just 1, okay? So the derivative of y is really just 1 as well, but with respect to y, okay? So the dy just means with respect to y. It really means the differential, but we'll read it as with respect to, okay? So the differential of y is just 1 with respect to y. Now, whenever it's 1, it's really not necessary, so I'm going to go ahead and get rid of that there, okay? So here we go. The derivative of x squared is 2x, but the differential of x squared is 2x, but with respect to x. Okay? The derivative of 3x is just 3, but the differential of 3x is 3 with respect to x. Okay? And the derivative of 2 is just 0 because it's a constant. So the differential of 2 is still just 0, and it has no variable there, so we don't need a differential. Okay? So first step, we take the differential. This is what we call taking the differential. It's just the derivative with respect to the variables. Okay? The next step, which I'll write in blue, is we're going to divide every differential by a dx. All right? The reason why we do that is because dy dx is your y prime. Okay? But I'm not going to write that. So this is going to give me dy dx is equal to, I notice that dx divided by dx just goes away. And I'm going to be left with 2x plus 3. And that is my derivative. That is my instantaneous rate of change. That is my slope of a tangent line. Okay? Now, wouldn't it have been easier to just take the derivative? Y prime equals 2x plus 3, and then I'm on my way. Right? So when it's explicit, it's easy to just take the derivative. Okay? But for the sake of learning differentials, I'm showing you guys how this works here, okay? You take the differential, then you divide by dx. Okay? It seems redundant when you're doing the differential on an explicit equation, okay? But this is just so you guys get used to what a differential is, okay? So humor me here, okay? Here's part B. We're going to go ahead and take the differential and then find the derivative after, okay? Okay, so we have y equals 3x to the 5th plus 4 divided by x. Obviously, this is explicit, but we're going to do differentials anyways. But before we do that, I am going to rewrite 4 divided by x so I can avoid the quotient rule. Pause and play here. Think about what you would rewrite 4 divided by x by. Okay, this should be 4x to the negative 1. Okay, this way you could avoid the quotient rule. Okay, now this is not the derivative, so I'm going to call this y. Okay, now that everything's in place, I'm going to take the differential. The differential of y is just 1 with respect to y. The differential of 3x to the 5th is 15x to the 4th with respect to x. And here, think about what that comes out to. Press play when you're ready. It's going to be minus 4x to the negative 2 with respect to x. Okay, it's minus 4 because that negative 1 is brought down. And then you subtract the exponent by 1. Okay? Now that you've taken the differential, we're going to divide every differential by dx because we want dy dx, okay? So dy dx will now equal 15x to the 4th, the dx's cancel out, minus 4x to the negative 2 or 4 over x squared if you want. Okay, but again, it's a lot easier to just take the derivative here because it's explicit. All right. So what would happen if you didn't have an explicit equation, right? So for instance, this one. Here's example 2. Okay. So 1, it's implicit. We know that because there are multiple variables on one side. Okay. And some of you may argue, well, we can totally rewrite this so that's not implicit anymore. Absolutely, you can. Okay? But I'm going to tell you guys right now on the AP exam, as well as my exams, when they give you something implicit, they will give you something that you cannot fix. Meaning, it's virtually impossible to rewrite it so that you can solve for y. And I'll show you some examples later on, okay? Okay, so here's what we do. We're going to go ahead and take the differential. Okay, So I'm going to start off with the right-hand side here. And notice how I left a lot of space. The differential of 1 is just 0. 1 does not have a variable here, okay? So there's no need for a dx or a dy here because there's no variable. But on the left-hand side here, notice how that's x times y. How do you take the differential or the derivative of a product, right? We have to apply the product rule. So here we go. So the product rule is the first times derivative of the second plus the second times derivative of the first. The differential is the exact same thing, but we put respect to that variable. So here we go. We'll do the easy part first. So we take the first times the differential of the second plus the second times the differential of the first. Notice how I took care of all the easy parts, okay? Okay, so the derivative of the second, the derivative of y is just 1. So the derivative or the differential of y is just 1 with respect to y. You could put that 1 in there if you guys want. Now here, the differential of the first is just 1, but with respect to x now. Okay? Again, the 1s are not necessary, but I'll put it there for now. Okay? Now what we're going to do is we're going to divide every differential by a dx. So here I have two differentials. So I'm going to divide this by a dx, divide this by a dx. Technically, what's happening is you're also dividing by dx over here, but 0 over anything is just 0, okay, unless it's 0. Okay, here's where it's a little bit different now. If you notice in the last two problems, if we wanted to find the derivative, we needed to end up with the derivative, which is dy over dx. dy over dx was conveniently isolated, which is why explicit functions are easy, because y is already by itself. So when you take the derivative, dy dx is by itself. But now here, dy dx is right here. It is not isolated. So there's one more step to it. We have to move some things around, okay? First off, dx over dx is just 1. So I'm going to write it out again. We have x times dy dx plus y times 1, which is just y. All right. What you guys want to do here is you want to solve for dy dx. Okay. It looks really weird right now because there's a lot of variables, but just imagine that dy dx is a giant variable. How do I get this orange variable by itself? All right. So the first thing you would do is you would subtract your y on both sides. Okay. So now x times dy dx is equal to 0 minus y is just negative y. Okay. And to get dy dx by itself, I would have to actually move that x there. So since it's multiplying, I'll divide by an x. And I'll divide by an x. So the third step here is isolate. All right, so dy dx is negative y over x. Notice how our answer is also implicit. Okay? So, for implicit, we take the differential. Okay? Then we divide by a differential. Then we isolate dy dx. Okay? It's 5% calculus, 95% algebra. So you guys are pretty much refreshing and strengthening what you guys know about your algebraic skills, okay? Remember that dy dx is just the slope of a tangent, okay? The instantaneous rate of change. So just keep that in mind. Okay, here we go. Here's part B. Okay, write that down, okay? If x squared plus y squared equals 25, find dy dx. I should have wrote the instructions up here too. Find dy dx. Okay. You guys could try this on your own. If you get stuck, press play again. If you're done, press play. But go as far as you can. Don't worry if you make a mistake. I'd rather you guys make your mistakes now. Okay? Okay. First off, clearly this is implicit. We have multiple variables on one side of the equation. Okay? So we'll take the differential. Okay, the differential of 25 is just 0, no variable there. The differential of x squared is 2x with respect to x. The differential of y squared is 2y with respect to y. Okay. So now we took the differential. What do we do next? We divide by what we want, dx. And technically it happens over here too. Okay, but 0 over dx is just 0. Okay, so what we have so far, 2x dx over dx cancels out. We're just left with 2x here. We have a plus 2y dy dx equals 0. Last step is to get this dy dx by itself. So naturally, what would be the first thing that you guys want to move? Pause and press play when you're ready. We want to go ahead and subtract this 2x here. So now 2y dy dx is equal to negative 2x, because 0 minus 2x is just minus 2x. And then here, to get dy dx by itself, we divide by 2y. Okay, so dy dx will equal negative 2x over 2y, or if you simplify it, negative x over y, because you could definitely reduce out one of the 2's. Okay, we found the slope of a tangent line. We found the instantaneous rate of change. Okay, just the general slope, nothing specific here. Okay, so here this is just the general slope of a tangent. Okay, so here's part B, a follow-up to part A here. Okay, go ahead and write it down, press play when you're ready. Okay, now what they want you to do is they want you to find an equation of the tangent at this point. Does that ring a bell with you guys, right? So we were focusing a lot on this. How do you find the equation of a tangent line? What 2 things do you need? Pause and press play when you're ready to answer. Look back if you need to, okay? To make an equation of a tangent line, you need 2 things. You need a point and you need a slope. They already gave us a point, 3, 4. So all we need is a slope. How do I find the slope, right? Well, I know the general slope is negative x over y. But how do I find my specific slope, right? So what we want to do is we want to evaluate this slope at 3, 4. If you guys remember, the evaluate symbol is this vertical bar here. We're going to evaluate this at 3, 4. So notice here, you could actually plug in the x and the y. So this is really negative 3 over 4. That is your specific slope. So exactly at 3, 4, your slope is negative 3/4. Okay. Do we have everything we need? We have a point. We have a slope. Yep. So here we go. Y minus y1, which is 4, equals the slope times the quantity x minus the x coordinate. Point slope form, you don't have to rewrite it into slope intercept. Okay, so be careful when you guys are looking at the answer keys on Slater or in the back of the book. Sometimes they go all the way to slope intercept form there, okay? And that's it. Okay, we found the slope of the tangent line at that point. Let's try another one. Let's call this part C. Okay, by now you know that Mr. Lee cannot recall which example is which, so he loses count all the time, and he likes to talk in third person. Okay, here we go. Find y prime if x cubed plus y cubed equals 6xy. Okay, so remember y prime is the same thing as dy dx. They're asking us to find dy dx here, okay? Okay, so here we go. I'll bring down my equal sign. Okay, let's take care of the easy part. The differential of x cubed is 3x squared with respect to x. Plus the differential of y cubed is 3y squared dy. Now on this right side here, I notice that I have a product, 6xy, right? Now, we have to apply the product rule. You can handle this in two ways. It depends on how you see it. You can treat the 6 as if it had nothing to do with the product. Or you could treat it as the 6 is with the x times the y. It really doesn't matter which way you do this here, but I'm going to go ahead and choose this route, where 6x times the y. So here we go. Okay, so 6x, I'll look at this as 6x times y. So since we have a product, this is going to be the first times the differential of the second plus the second times the differential of the first. I could have easily filled in the blanks along the way, but this is how I make it less overwhelming, okay? The differential of the second is just 1 with respect to y. The differential of the first is just 6 with respect to x. Number one mistake I see people making is they forget to put the differential. Okay? Okay, we took the differential. What's next? Right? Let's choose a different color. Cool. We're going to divide every differential by dx because we want y prime, and y prime is dy dx right here. But notice how it's also right here. What the heck, right? Let me get rid of all these lines so I don't confuse you. Okay, so we're dividing everything by dx. Let's clean this up here. Dx goes away here and here. So I have 3x squared plus 3y squared dy dx equals 6x dy dx plus y times 6 is just 6y. Okay, to make this a little bit easier to understand, we're doing something similar to this, like in a separate problem, you guys. So sidebar. If I told you 5 plus 4x equals 2x plus 6, how would you guys solve for x, right? How would you solve for x if you have variables on both sides of the equation? So naturally, people would try to bring it over to one side. Okay. And then they would start isolating, right? So we're going to do the exact same thing here. I noticed that we have multiple dy dx terms. We have one right here, but we also have one right here. So I'll show you the logical way, and then I'll show you a shortcut afterwards, okay? We're going to go ahead and subtract 6x dy dx on both sides. I'm going to bring over all the dy dx's on the left here, okay? And anything that doesn't have a dy dx, I'm going to move towards the right, okay? So here, I notice that a 3x squared doesn't have a dy dx, so I'm going to move that over here. So I'm going to go opposite, and then I'm going to go opposite. It looks like a lot, but it's not. So here's what we have. I'll write everything out. You guys are going to figure out your shortcuts in a second. So I have this canceled out and this canceled out. So I have 3y squared dy dx minus 6x dy dx equals 6y minus the 3x squared. Okay, so what I did here was I brought all of my dy dx terms to the left side and anything that doesn't have a dy dx on the right side. What this allows you to do now is you could actually factor out a dy dx because they have it in common. Now, if you take out a dy dx, you're going to be left with 3y squared minus 6x. Sound effects. here we go. Right-hand side, we're going to leave alone. Okay? How do I get dy dx by itself? You divide that sucker over. It's messy, but who cares? It's not our job. Okay? So, dy dx is equal to 6y minus 3x squared all over the quantity of 3y squared minus 6x. Although messy, it still is the derivative, the slope of a tangent line, the instantaneous rate of change. If you notice here, though, calculus occurs right here. That's your calculus. The rest is algebra. Okay? So you're really strengthening what you know about your algebraic skills. Okay? Don't worry if you're not there yet. If you are good with algebra, great. Work on your speed. Okay? But accuracy first before speed, you guys. Okay? So we found the general slope of a tangent line. Okay? Here's a follow-up to that same question. Part B. Find the tangent to the folium of Descartes. So this right here is a special name for this equation. Mathematicians got a little bit nerdy there and they gave it a name. But regardless, we're finding the tangent, the equation of a tangent line. How do we do that? We need two things. Pause and play when you're ready. We need a point and we need a slope. Go ahead and try that out, okay? Press play when you're ready. They already gave us a point 3, 3. And I know the slope is dy dx, but I need to evaluate that at 3, 3. Okay, so if I plug that in, I get 6 times 3 minus 3 times 3 squared all over 3 times 3 squared minus 6 times 3. This should come out to, oh gosh, what is that? 18 minus 27, negative 9 over 27 minus 18 is 9. That comes out to negative 1, which is your slope. Okay, do I stop there? No, we go one more step. So y minus y1 equals the slope times x minus the x coordinate. That is your specific slope here, and that is your equation of a tangent line at 3, 3. Okay? So this is pretty much what you guys will see for the most part, where you have multiple dy dx's. You got to bring them to one side, and then you got to isolate it. Okay? Okay. Here's part C. Try it out on your own. Go as far as you can. All right? Clearly, this is implicit. We have multiple variables on both sides. Nothing is isolated here. Okay, so both sides, you got to be very careful. Let's take care of the right side first. Clearly, that is a product, so we have to apply the product rule. So that's going to be the first times the differential of the second plus the second times differential of the first. Okay? Okay, so the differential of the second, the derivative of cosine x is just negative sine x. Practice this, you guys. Assuming that we have to take this in person, you're not going to have these formulas, okay? The derivative of cosine is negative sine x, so the differential is going to be negative sine x dx. Okay? The differential of y squared, the first, is just 2y with respect to y. Don't forget those differentials. Okay? Now, how the heck do you take the differential on the left-hand side here, okay? Think about what you would use. Notice how there is a function inside of a sine function. We call that a composition. How do you take the derivative of a composition or a function inside of another function? We have to apply the chain rule. Okay? The chain rule is the derivative of the outside. Derivative of sine is cosine. The derivative of the outside of the same inside times the derivative of the inside. What is the derivative of x plus y? The derivative of x plus y is 1 with respect to x plus 1 with respect to y. Again, you don't have to put the ones, but I'll leave that there. Replay that a couple times, okay? This gets a little gross, but you guys got this. Okay. We'll go ahead and these are cool colors. Okay. We'll divide every differential by dx. Here, I'm counting that we have 4 differentials. 1, 2, 3, and 4. Okay. I'm going to take this one step at a time so that we don't lose focus here. We have cosine of x plus y times 1 plus 1 dy dx. You can put the 1 there if you like. Equals, I'm going to scoot that negative in the front here because it's all multiplying. Negative y squared sine x. Dx over dx goes away. Plus 2y cosine x dy dx. Now, if you wrote cosine x 2y, that's fine. I like to just put the terms in the front and the trig functions last so we don't confuse it. Because if you write it like this, it kind of looks weird, right? So I'm just scooting this in the front. Again, it doesn't matter how you write it. Okay, so let me give you a similar situation so you understand what to do here. What if I gave you guys 4 times 1 plus 3x equals negative 6 plus 5x? If I gave you this separate problem here, what would you do first, right? Pause and press play when you're ready. First thing you would do is you would probably distribute that. And that's a good first move. That's exactly what we're going to do here. We're going to take this blob of a quantity, cosine of x plus y, and we're going to distribute it to the 1 and to the dy dx. So cosine x plus y times 1 is just cosine of x plus y. Is that hurting your eyes? Oh my gosh, it's playing tricks on me. Plus cosine of x plus y times dy dx. Okay, let me get rid of this so that you guys don't get confused. Okay, equals, the right hand side I'm not going to touch. And then now we're back to what we had in part B. Okay, where we had dy dx's on both sides of the equation here. So what we want to do is we want to bring everything towards the left. So now I'm going to write out the steps, but then I'll show you how to cut corners here, okay? So to move this over, I have to go opposite. So minus 2y cosine x dy dx minus 2y cosine x dy dx. Okay, but anything that doesn't have a dy dx, I'm going to move over. So let me subtract cosine of x plus y here, and I'll subtract cosine of x plus y here. So opposites will cancel out. Okay, one thing I want to say is just because you're writing a lot doesn't make it complicated. You're performing the same steps. So don't let the amount that you're writing out determine its complexity, okay? You just got to be a little bit organized. That's all it really is. So here we go. We have cosine of x plus y, okay? dy dx minus 2y cosine x dy dx equals negative y squared sine x minus cosine of x plus y. Okay. I'm going to factor out a dy dx. I'll be left with cosine of x plus y minus 2y cosine of x equals negative y squared sine x minus cosine of x plus y. All right. Then I'm just going to divide that guy over. I'm not going to finish this one up, but there's your answer. That is your general slope of a tangent line, okay? Okay, so how do we make things a little bit simpler? So this is the last one for the day, all right? Okay, so here's what we do. We have go ahead and write that down. Find dy dx. Okay, go ahead and take the differential there, and then I'm going to show you some shortcuts. Okay, so we have here, we have 4x cubed dx plus 5y to the fourth dy. Okay, 24y to the fifth dy minus 6x squared dx. Okay, here's how we speed things up, okay? We divide by dx at every differential. Okay, so if you guys watch other videos, okay, they will teach it a little bit differently. And I've seen that before, and from my experience, this works best. So please follow it, okay? DXs are going to go away. I have 4x cubed plus 5y to the fourth dy dx equals 24y to the fifth dy dx minus 6x squared. So here's what you do if you want to save time, all right? And you got to be careful with it. Now, if you don't see what's going on, I encourage you to just write out the steps. Let's look back. We brought over, I'll highlight it so you can see what I'm talking about. We brought over the dy dx's towards the left. And then we brought all over the non-dy dx terms to the right. Okay? Then we wrote it out. Then we factored out a dy dx, and then we divided it over. Okay? So let's save some time here. Okay? What we're going to do is I am going to bring it over, but I know that I'm going to factor it out as well. Okay? So here's what happens. I know that 5y to the fourth is staying on the left, so the sign will stay the same. I know that I'm going to bring a 24y to the fifth over, so I have to go opposite and subtract 24y to the fifth. Okay? That is how you skip a bunch of steps. Now on the right side, negative 6x squared stays there, but 4x cubed is going to go opposite. Okay? And then you divide. Some of you can jump all the way to the very last answer if you wanted to. I'll leave that up to you guys. 5y to the fourth minus 24y to the fifth. Okay, and there's your answer. Wherever you see you can cut corners accurately, go ahead and do so. Okay, but that's pretty much it. We were able to differentiate implicit equations using differentials. Okay, so notice how the product rule, the quotient rule, the chain rule, that doesn't go away. Everything that you guys have been learning still applies. Okay, practice it. Let me know what you think.